Have you ever just looked up at the sun and thought, how does that thing work? It's not a giant ball of fire, it's actually a colossal nuclear reactor. And for decades, the ultimate dream has been to build a tiny version of it right here on Earth. So let's dive in and see just how close we are to actually bottling a star for clean, limitless power.
I mean, this phrase just says it all, doesn't it? It captures the almost magical promise of fusion. The basic idea is taking one of the most common things on our planet, water, and turning it into the same clean, powerful energy that lights up the entire universe. It sounds like something straight out of science fiction, but it's quickly becoming scientific fact.
And yeah, that really is the million-dollar question, isn't it? See, stars have one huge advantage we don't: gravity. Their own massive weight does all the work, crushing atoms together. Down here on Earth, we have to get a whole lot more creative. So in this explainer, we're going to break down exactly how scientists are trying to pull off this incredible engineering challenge.
All right, first things first. Before we talk about building one, we really need to understand what it is we're working with. Let's get into the science of fusion. You could think of it as the universe's ultimate energy trick.
Okay, so here's a way to think about it. You know how if you take two strong magnets and try to push their north poles together, they fight you? They repel each other? Atomic nuclei do the same thing. Fusion is all about getting those nuclei so incredibly hot and moving so ridiculously fast that they overcome that repulsion and just smash together. And when they fuse, a tiny bit of their mass vanishes and gets converted into a huge burst of energy. Now, it is absolutely crucial to get this straight. Fusion is not the same as the nuclear fission we use in power plants today. Fission is about splitting big, heavy atoms apart. That process can create dangerous chain reactions and nasty, long-lived radioactive waste. Fusion is the complete opposite. It builds small atoms up. And here's the key. If anything goes wrong in a fusion reactor, the reaction just stops. That's it. No meltdown. It's what makes it fundamentally safer and cleaner.
So what's the fuel for a man-made star? Basically, it's special types of hydrogen. The two main ingredients are deuterium, which we can get easily from seawater, and tritium, which we can make from lithium. And get this fact always blows my mind. The amount of deuterium in a single glass of regular old seawater has enough energy to power a home for an entire year. The fuel is, for all practical purposes, limitless.
Okay, so we know what it is and what it burns. But how in the world do you actually build one without a star's worth of gravity to help you out? Let's get into the cosmic recipe scientists are trying to perfect right here on Earth. It really boils down to four main steps. First, you take hydrogen gas and turn it into something called plasma, a super hot soup of particles. Second, you crank up the heat to a level that is just hard to even imagine. We're talking 150 million degrees Celsius. That is 10 times hotter than the core of the actual sun. Third, and this is the really tricky part, you have to somehow hold on to and contain that plasma. And finally, you capture all the energy that comes off to make electricity.
Right, so how do you hold on to something that's 10 times hotter than the sun? You obviously can't just put it in a box. There are two main ways we're trying to do it. The first is called magnetic confinement, which is basically an invisible magnetic bottle. It uses powerful magnets to hold the plasma in a donut shape. The other approach is called inertial confinement. You can think of this one as a laser hammer. It uses almost 200 incredibly powerful lasers to blast a tiny pellet of fuel, crushing it so fast that it ignites.
Now you know, this incredible science didn't just pop up overnight. It's been a long journey, a scientific marathon, really, that started over a century ago with just pure curiosity about how stars work, and is now turned into a global race against time.
And looking at this timeline, you can really see this story unfold. The idea sparks in the 1920s, we get the first key machine, the tokamak, in the 50s, we see the first little bursts of real power in the 90s, but then, look what happens when we hit the 2010s. Suddenly, private money starts pouring in, innovation just explodes, and then, bam! In the 2020s, we finally hit the big one, the tipping point.
Yeah, that tipping point is why you're hearing so much about fusion right now. For the longest time, there was this running joke in the science world that fusion power is always 30 years away. Well, guess what? It's not a joke anymore. Let's look at what changed. Everything, and I mean everything, comes down to this one simple symbol, Q greater than 1. This is the Holy Grail. It's a moment called ignition or break-even, and it just means you got more energy out of the reaction than you had to put in to start it. And for the first time in human history, we finally crossed that line.
And here it is, the date for the history books, December 2022. Using that laser hammer method we talked about, the National Ignition Facility in the US
did it. They achieved ignition. Sure, it was just for a split second, a tiny flash, but that didn't matter. It was proof. Proof that bottling a star and getting more energy out than you put in was actually possible.
And that single breakthrough, it opened the floodgates for investment. We're now talking about over $6 billion in private money pouring into more than 40 different fusion startups. This isn't just a government science project anymore. Oh no, this is a full-blown commercial race to the finish line.
And this race is happening all over the world. You've got the enormous International ITER project, which is a massive public collaboration. You have NIF in the US trying to perfect its laser tech. And then you've got these smaller, nimbler private companies like CFS who are aiming to have a prototype plant on the grid by 2026. Plus, you have national programs in places like China setting their own records. It's a truly global sprint.
So, with all this momentum, does this mean a fusion-powered future is right around the corner? Well, let's pump the brakes just a little. It's time to take a clear-eyed look at the very real hurdles, the hype, and the incredible hope that's driving all of this.
Look, achieving ignition was a massive scientific victory, but now comes the really hard part, the engineering. And these are not small problems. We need to figure out how to keep that super hot plasma stable for long periods of time, not just a split second. We literally have to invent new materials that can withstand a constant barrage of intense radiation day in and day out. We also have to make the reactor breed its own tritium fuel so the whole thing is self-sustaining. And of course the big one, we have to bring the enormous cost of these first plants way down so they can actually compete.
But the reason everyone is pushing so hard to solve these problems is because the prize is just about everything. A power source with virtually zero carbon emissions, a practically endless fuel supply, a system that's inherently safe with no risk of a meltdown. It's a technology that could end energy scarcity for good and reshape global politics.
You know, I think this quote just nails it. It's not a silver bullet, and there is a ton of hard work still to do. But the potential, the ability to fundamentally change our world for the better by literally turning seawater into sunlight, it's so profound, it really does feel like magic.
So we're at this fascinating moment in history. The science has been proven. The engineering race is officially on, and the destination is a clean, abundant energy future for everyone. The only question left is, can we put all the final pieces of this cosmic puzzle together in time?